Thanks for coming to this talk. My name is Amr Awadallah. I am one of the founders for Cloudera. Also the Chief Technical Officer. And today I'm going to tell you the story about Hadoop, why it came to be. I'll tell you my experience with Hadoop because I used Hadoop in a previous role before I co-founded Cloudera. But before I do that, I wanted to get a show of hands from you. How many people heard the word Hadoop before today? Okay, that's good, that's good. 80%, I would say, almost 90%. That's great. So how many of you used Hadoop or are using Hadoop in the organization? Okay, that's not good. We want to change that.
This is why we are here.
So before Cloudera, I was at Yahoo, Yahoo.com for 8.5 years. And my co-founder, Jeff Hammerbacher, he was at Facebook. Both myself and Jeff, we ran business intelligence and data analytics teams at these two different organizations. And we experienced new types of headaches, new types of problems with data that kind of made us need to look for something new. And that's when we stumbled across Hadoop. The headaches we experienced are covered in more detail throughout the presentation, but the headaches we experienced can be categorized as these four things. Number one, we had data that was growing very quickly, right? So every day we had more data than the previous day. So that's the big part of big data, is the size of the data, but it's not everything. The other problem we experienced was we had data of many different types and forms. So it wasn't just data that fits very nicely in relational tables, very well structured relational tables, but it was data that was images, that was videos, that was XML, Apache log files, web crawls, email, text, etc., all different types of data being thrown at us. So that's number two, right? So number one is the volume aspect, number two is the variety aspect, meaning different types. And then number three was, even for the structured part of our data, even for the relational part of our data, the structure wasn't fixed, the schema wasn't fixed. The schema was changing all the time. Continuously, we need to add more dimensions in our models and more attributes. So we need to be able to have a schema that can evolve very, very quickly. And then last but not least, and this is more of it's not a technology thing, but it's more a human kind of social phenomenon, is we as organizations at large, we're starting to look at data more than just a dashboard. Data is no longer just this dashboard that we show to our CFO once every quarter or our marketing officer once every week. Rather, data is a true asset that needs to be exploited in a new way. And that was kind of something that Yahoo was pushing very strongly. Facebook also was pushing very strongly as well. So it's these four things, right? Size of the data, the variety, the different types of data, the rate at which the data is changing, and then the fact that data is no longer just this thing we run a report on. It's more than that. We need to be able to run much more deeper analytics and applications on top of our data. So with that, at that time, that was about 7 years ago. When I was still at Yahoo and Jeff was still at Facebook, we looked around the market and we couldn't really find something that works. Like there was lots of technologies like relational database management systems, storage systems, high performance compute systems, and in every case we felt as if we had this very thin straw with which we have to access the data, right? And we were dataholics. We wanted to jump in and just access everything. We didn't want to be limited by this thin straw. And that's when we stumbled across Hadoop. Right? And that's why I'm going to tell you the story about Hadoop today. So the underlying trend is this one, right? The underlying trend, actually there's two trends. There's this one and there's the hardware technology trend, which I'll describe briefly after this. But this trend is essentially the trend of the massive growth in what we call unstructured data. And when we say unstructured data, we really mean non-relational data, right? So relational data, as you can see, started with the advent of relational database management systems 40 years ago, and has been continuously growing. And relational data is really about explicit human transactions. It's about explicit bank transfer. It's about an explicit credit card swipe, an explicit purchase from a point of purchase, etc., etc. So it grows at the rate at which humans grow, relatively speaking, and which is not a very, very high rate. Unstructured data is about implicit transactions. So it's not just the explicit purchase I made, but it's everything that was around that purchase, right? So unstructured data is about tracking everything, not just the explicit action that took place. Tracking every single link you saw on a web page when you visit a website. Tracking the power consumed by your house with smart energy meters at the second level, not the week level or the month level. And not just at the second level, at the device level, how much power is being consumed by every single device in your house. Tracking your mobile device and its location and which applications you're using, and how much power each application is consuming so we can further fine-tune these applications, etc. There's just so many implicit actions that we as humans generate because of the machines around us. And that advent of the mobile internet, which I'm sure Mike Saylor gave you lots of speech about how mobile is going to change the whole world. That advent of mobile internet and our sophistication as humans and how we instrument everything is leading to this wave. Is leading this humongous wave of complex data that's coming at us from left and right. And we need something new to be able to absorb and analyze and deal with all of that. Second, the hardware, actually, the technology changed as well. Like in the old days, we had the CPUs, and every year we would just buy a bigger machine with a bigger CPU and more multi-core inside that same machine, and 16-way, 64-way, and et cetera, et cetera. And that trend has been flipped over its head over the last 10 years. So over the last 10 years now, the movement is towards commodity hardware, right? We can buy this, we call them pizza boxes, the very thin 1U servers. And these very thin 1U servers, they now can have 12 hard disks. Each hard disk is 2 terabytes. That's 24 terabytes in 1U. And we can have many, many cores inside them. So the power of the commodity server went up by leaps and bounds over the last few years. So these two trends coupled together is what's leading to this technology that I'm talking to you guys about today. So before I jump into Hadoop itself, I wanted to share with you my story at Yahoo in more detail. So I actually gave a keynote here at Microstrategy World, not in Amsterdam, but I think it was in Miami 3 or 4 years ago. When I was still at Yahoo, I gave a keynote about our infrastructure at Yahoo, and this is what the picture looked like back then. Essentially, and I think this is the picture everywhere, right? Is you have an instrumentation layer and a collection layer where you get the data from all the different parts across your organization. And then you typically copy all of that data into a storage-only network, like a NetApp farm or an EMC farm. And then you have an ETL system that sits on top of this layer that extracts ETL, right? Extracts the unstructured data, transforms it from unstructured to structured, and then loads it into a relational database management system like Oracle, Teradata, et cetera, et cetera. And then on top of that, you have your BI, your MicroStrategy, and your interactive applications running on top of the relational database. So this is the model that exists everywhere, and that's the model we had, right? Before the new headaches that I described start to show up. And then we were fine moving along with this, but then we got hit by these three things. Is number one, we wanted the ability to go back and ask questions from the original raw data. Because when you go through transformation, when you create your conform dimensions and your surrogate keys and all that kind of stuff, you actually lose fidelity. You lose data when you do that. So to give you a concrete example, in web systems, when you use a browser like Firefox or Chrome or IE, they pass this thing called the user agent string. The user agent string is a very long text string that describes which OS you are using, which version of that OS, which browser you're using, which version of that browser. But it's structured in a very long, unstructured string. And typically what we do in our data marts is we have an ETL rule that parses that string and populates 4 dimensions. The 4 dimensions we populate are the browser dimension, and we have the surrogate confirmed keys for the browser dimension, the browser version for each browser dimension, for each browser attribute, the OS and the OS version, right? So we parse the string, populate these 4, and that happens. So down here we have the original string, and up here we have the parsed 4 columns for the 4 attributes. And the ETL logic does that transformation. So the problem we had this was working very nice, and we had the Firefox defined, and we had the IE defined, and so on, and the iPhone came, right? And the iPhone grew so quickly, and we didn't have the parsing logic for the iPhone OS and the iPhone browser. And the business came back and asked, so we want to see how quickly the iPhone traffic is growing across Yahoo Sports, and across Yahoo News, and across Yahoo Finance, and across Yahoo Search, etc., etc. And of course we told them we can't, right? We don't have that. That we have this thing called undefined, which was the lump of everything that we never saw before for the last 6 months. So the only way to answer that question with our existing architecture like this one is we have to go back and redo the ETL for the last 6 months to reparse all of these strings and repopulate the cubes inside here to be able to answer that question. Versus if this layer here, if this layer that was storing our raw, unfettered, high-fidelity data was a smart layer that can compute as well, then I can simply just ask the question of this layer, get the answer to the question, and then later on figure out how to get it to be part of my official dimensions if I need to do that. So that was really one of the very, very key problems, is the ability to access our original, unfettered, high-fidelity data. The number 2 problem is one that we're all very familiar with, which is hitting the ETL window, right? So at Yahoo, the day ends at 12 p.m. Pacific. Before 9 a.m. the next day, we had a contract to the businesses, we'll have all the cubes ready for you, right? So that on 9 a.m. the next day, you can see the reports for the previous day. That means we have 9 hours to finish all of our transformations. And because of the nature of how quickly the data was growing, we were very quickly hitting that ETL window. We couldn't get this grid to scale because of this old architecture of having the computation on one side and having the data on the other side stresses the network infrastructure. The network infrastructure is not growing at the same speed at which machines are able to grow. So the solution there obviously is you want to push the computation to happen right beside the data, not move the data to the computation. So that's number 2. Is the ETL window. And then number 3, which is a problem which is very dear to my heart, is we ended up killing our data. And the way we killed our data is, obviously we have data here, which is a system that can store but can't compute. So we can't extract the value of the data. Once it has moved here, then we can get the value from there, but down here we can't. So we end up imposing retention windows. We say we can only retain stuff down here for 6 months. Anything older than 6 months, you archive to tape. And we all know, once you archive stuff to tape, you just don't see the data. It goes there, it never comes back. So the reason why, obviously, is archival systems, and it's not just tape, it's Blu-ray and so on. Archival systems are extremely economical and cheap for storage, but very expensive for retrieval. It's very hard to get stuff back from them. It takes an act of God or government to get things back from tape. So we want to solve these 3 problems, right? We wanted to have the ability to go back and run analytics on our original unfettered data. We wanted to be able to scale our ETL, and we wanted to be able to keep data alive for much longer. And that's pretty much what Hadoop allowed us to do, right? So Hadoop is this single layer that combines your computation engine with your storage engine, right? So now you have this layer that can do both your storage and your compute in a single layer, side by side, using the same hardware, using the same commodity servers, bringing lots of optimizations in terms of what we call data locality to try and minimize network bandwidth and so on. But by having that, we now solve all 3 problems. By having this, we are able to go back and ask questions from this layer now, because now this layer becomes smart like this layer, right? So you can ask questions of it now, of your unstructured data, in the same way that you're asking questions from your cubes up here. You're able to do your ETL much more scalably, and I'll talk more about that later on. And you're able to keep your data alive for much longer because of 2 things. One, you're now able to extract value from them so you can justify keeping them. But second, Hadoop, because it uses commodity hardware, brings down the economics of storage and computation to a level that you just haven't experienced before. And a terabyte in Hadoop, including the money that you pay to a company like Cloudera for maintenance, because Hadoop is open source and free, as I'll talk about that later on. A terabyte, including the hardware, the people, the money you pay Cloudera, etc., costs around $400, $400 per terabyte. That's compared to anywhere between 10,000 to 100,000 in other systems. So that ability to bring down the cost significantly reinforces how long you can keep your data around. So what is Hadoop? You all raised your hands, so I guess you all know that Hadoop is an elephant, right? And the reason why Hadoop is an elephant, and it has this nice, cute elephant up there, is the creator of Hadoop, his name is Doug Cutting. And Doug Cutting created Hadoop based on papers that Google have published in 2004, so that's 7, 8 years ago. And Doug Cutting, his son, at the time, was 4 years old. And his son had a nice plush elephant toy, yellow elephant, like that one. And out of the blue one day, unprompted, his son literally started calling that toy Hadoop. He made the word up. He literally made the word up. And his dad picked up that word and he made that word the name of the project. His son today is 11 years old and he's very proud of his accomplishment. So what Hadoop is a data operating system. That's how I describe Hadoop. It's a data operating system. So what is an operating system first? We need to understand that. An operating system like Windows, like Linux, like Mac OS, like FreeBSD, for those who still might be using it, it does two things, right? Any operating system in the world does two things. And these two things are what? Are store files, run applications on top of files. That's what an operating system does. If you go back to DOS from Microsoft many, many years ago, that's what it did. Store files, run applications on top of files. You have many things around that core, around that kernel for device drivers, for UI, for security and so on, but the core of the system is store files, run applications on top of files, and that's exactly what Hadoop does. That's exactly what Hadoop does, with the difference that Hadoop does that on top of many, many servers. So Hadoop is about taking many, many servers and virtualizing them to look like one large file system that can store as many files as you would like, with one large application running framework for running applications on top of that file system in a scalable way. So that's what Hadoop is. Another way I describe that sometimes is I say it's the opposite of VMware, the opposite of visualization. So maybe if I can get a show of hands, how many of you know about VMware? Heard about VMware, the company? Good. So you will relate to this very well. So VMware, what they do is they take a real server, a real physical server, you run the VMware software, and then inside that physical server, you now have many small virtual servers, right? That's what VMware does. Hadoop is the other way around, right? Hadoop is about taking many, many physical servers, and then you run Hadoop on top of all of them, and then they look like one big, massive virtual server, right? So it's about that kind of abstraction. So at the heart of Hadoop are these two subsystems for doing these two things, for storing files and running applications on top of files. So the system for storing files is called the HDFS, the Hadoop Distributed File System. And the system for running applications is called MapReduce. That's it. Now there's many other things around that, around the kernel, that make the kernel more powerful, and I'll talk about that later on. And then there is these three key business values: flexibility, scalability, and economics, which I'm gonna talk about right now. So this, by far, is the key value and the key benefits that you get from Hadoop, right? And it's about what I call flexibility and agility, right? It's about being able to evolve and adapt and grow at the speed and the speed of the change of your data. So relational database systems follow a model that I call schema on write model. And by the way, this is the litmus paper test for how we can tell, is this a relational database or the new Hadoop big data kind of system? In relational database systems, you have to create a schema first before you can put any data inside of them. You have to say create schema, the columns, the names of the columns, the types of the columns, and then you have to go through a very explicit load operation that converts the data from its original format it came in to the native storage format of that database. And then you can store the files eventually once you do that. And that has benefits, obviously. When you do that and you pay the cost of transforming the data and laying it out at write time, you're able to get much more quicker interactive queries going through your system. However, by doing that, that means if any new data starts to come, and that new data doesn't exist in the schema already, does not have a dimension it can fit in, does not have a fact table column it can fit in, where does that data go? It doesn't go. It just gets dropped on the ground. It doesn't make it into the database, right? So you have that problem, and it doesn't make it until you add the rule that knows how to. You need to add actually 3 different places. You need to amend your BI tool data model. You need to amend your schema in your database, and you need to amend your ETL to absorb that new information that just came in. Now, the other thing, and this is a human problem more than a technology problem, is standards and governance. It's both a good thing and a bad thing. So it's a good thing in the sense that when you have a very fixed schema that only change once every couple of months, then you have a well-defined contract across every single organization in your company. Makes it very easy for people to talk to each other. They know what the schema is and so on. So it's good, that's good. However, it's also bad. And the reason why it's bad is because it inhibits innovation and it inhibits agility. Is that when I was lucky at Yahoo, when I had a new column I needed to add in one of my data models, I had to wait anywhere between 2 weeks when I was lucky, but more practically 6 months. 6 months until I get approvals from every single department that yes, we agree this is a good thing to do, right? The governance process, the compliance and governance process. And there's a good reason for that is they all want to make sure that this pristine schema that we have only gets affected in a way that everybody agrees on. However, it's bad is by 6 months. The reason why I want to add a column will be gone, right? I mean, the business reason why we need to do that analysis is gone. So we need to have both. We need to have the agility of a system that allows the schema to evolve very quickly and at the same time have the pristine model of a very fixed schema that only changes once every 6 months. So Hadoop employs what I call a schema on read model instead. So Hadoop says we're going to try and bind the schema at the latest point possible. So when you're loading data into Hadoop, you're actually not loading data, you're copying data. You're literally copying the data in its original native format, came in. You're copying the XML file, you're copying the database dump, you're copying the mainframe data dump that you got, you're copying the Apache log files as they came out of Apache. It's a file system as its heart. So you copy the data in whichever format you would like, it doesn't care. And it gets stored in that same format. It's not a proprietary storage format. It's the format that the data came in. And then, what happens is at runtime, when you're actually doing your computation, that's when a special program runs called a serializer, deserializer, or SERDE for short, that translates that data from its original native format into the schema that you care about as an analyst. And in fact, each one of us can have our own view. Like, we don't have to all have different schemas. That schema that we bind at query time can be different. So if I care about, as I said earlier, if I care about the iPhone browser user agent, then my parser will expose that. Somebody else who doesn't care about that yet will not see that. So you have that flexibility of binding the schema very late, gives you lots of flexibility and agility. So I use a layman example to describe this concept. Imagine, I don't know why there's noise coming up right now.
It's gone now.
Okay, it seems like this wire is...
Don't touch it.
There you go. So imagine two kitchens, right? There is the kitchen, the relational database kitchen on the right over there. Actually, that's your left, on the left over there. And then there is the Hadoop kitchen on the right. In the relational database kitchen, you go in and you have a very good, you're the cook, and you have a very good minion. You have a very good helper for you. And that helper goes to the markets, they buy the ingredients for you, and they pre-cut, they pre-clean for you the tomatoes, the potatoes, the pieces of chicken, the cubes of meat, etc., etc. Right? They do all of that work, which is the ETL work, right? So they pre-cut for you the schema that you're going to cook with. Now you as a cook, you'll be able to cook very, very quick, right? Because you already have all of the ingredients laid out for you. However, the only meals you'll be able to cook and the only questions you'll be able to answer are the questions that were pre-thought of by that helper that created that schema for you, that created these pre-cut ingredients for you, right? So it limits your agility and your innovation. In the Hadoop kitchen, your helper is a very lazy guy. He goes to the market and just brings back the bag of potatoes and throws on you, and brings back the bag of tomatoes and throws it on you, and brings back the livestock, the actual cow, and gives you the full cow and the full pig and the full chicken. So it's very messy kitchen, right? However, that messiness, because you're binding the schema at the last minute possible, you now as a cook, you can innovate and create any meal you would like. You can invent a new meal that has a new taste, a new look, a new feeling, because you have access to all of the original raw ingredients. And then, once you find a repeatable meal, once you find the McDonald's, right? Assuming the McDonald's is such a very special creation, but once you find that, and it's repeatable now, and you want to make many, many, many of it, that's when you move it back into the other type of kitchen, because now you know you actually need to create this thing over and over again. So once you have a repeatable problem, then you move it to that kitchen where it makes sense to pay the cost of the pre-parsing at right time, at the time when you got the ingredients, as opposed to later on. So that's kind of a very high-level way of describing the different mentality of thinking between these two ways, and they're not they're not at odds with each other. They're actually complementary. You need both in your organization. You need both capabilities in your organization. So by far, like if there's one concept I want you to leave this talk with, if I meet you later on for lunch or in a hallway and I ask you what was that concept, it's this one. Okay, it's agility and flexibility. Now, there is many other benefits. There is still two other key benefits. One of them is scalability. Hadoop was built out of papers published by Google. It was built from scratch to work with this new wave of pizza boxes, right? With this new wave of commodity hardware servers that can work with lots of cores and lots of hard disks, and you have many of them. So it was built from the ground up to work with that technology. And it pushes the computation to be right beside the data, so it reduces the load on the network infrastructure, which is very important. So technology point of view is that it really scales way better than anything else. Not just really my words, it's proven to scale way better than anywhere else. Facebook has a single cluster. I think Facebook is giving a talk later today. I recommend you go to it. Facebook has a single cluster, single file namespace with 100 petabytes of data in it. 100 petabytes of data, single namespace. Like many companies would claim, oh, we have hundreds of petabytes of data, but it's 1 petabyte over here, another over there, and then you add them up and it's 100 petabytes. No, this is a single system, single namespace with all of that data, reliable, available, etc., etc. So it's proven to work at that scale. But separate from the technology scale, there's also the human scale, which is even more important in my opinion. The human scale is the same algorithms, the same queries, the same data structures that you used for 3 nodes are the ones you use for thousands of nodes. You don't need to rewrite your queries. You don't need to re-optimize your indexes. You don't need to give hints to your query to fetch the data in a different way. You don't need to repartition your data. It just scales with you. You just add more machines. That's all you do. And as you add more machines, the system intelligently spreads the data over more machines and spreads the workload over more machines. So that's another very, very key concept. It's the scalability of humans working with the system is much more effective, both from a system administration point of view, but also from a analytic capability point of view. So that's number 2 concept, is scalability. And then number 3 is the return on bytes. Return on byte is just like return on investment. Return on byte is how much value am I getting from that byte as a function of the cost of storing that byte. And I mentioned this earlier when I said if that value is less than the cost, you end up here, you go to tape and you're dead. We'll not see you again. And with Hadoop, because we're able to extract the value, number 1, but number 2, we're able to bring down the cost by an order or 2 orders of magnitude, we're able to move this waterline all the way down so that you now can look at all of your data. And that's a new concept to many of us. Like, what does it mean to look at all of my data? How can I change my business and do new things when I can access all of my data for like 11 years, for 12 years, right? And be able to model effects on a per user basis for such long time periods. So I'll give you a couple of examples, one from the web industry and one from the finance industry. From the web industry, Google actually published a very nice paper called The Unreasonable Effectiveness of Data. The Unreasonable Effectiveness of Data. I recommend that you guys go read that paper. It's a very short paper, a position paper. And in it, they explained essentially the concept that we refer to as data beats algorithm. If you are able to access all of your data, you will be able to achieve much more sophisticated and better results with much simpler algorithms, right? And they showed a couple of experiments. One where they had, for a small data sets, 2 algorithms, one really good algorithm, one mediocre, kind of simple algorithm. And yes, the really good algorithm did way better than the mediocre algorithm when you had a small data set. But when you apply a much bigger data set, the difference between the best algorithm and the okay algorithm shrinks. Right? The okay algorithm becomes just as good. The big data world, and this is actually what Google does, is that they don't do any of that. What they do is they look at the user sessions. Each one of us, they have millions of users. Each one of us, when we mistype a query, if we mistype a query and the did you mean thing doesn't show, then we're not going to click on any of the results because they will be the bad results. And then we will rewrite the query as humans to the right spelling. We'll recognize our mistake, we'll rewrite the query, we'll get the right spelling, and then we'll click on the results. So within a session, you're going to see a query, no clicks, a query that's very close to the previous query in terms of the number of characters and the layout of the characters, and then a click. And that's how we can tell. This query is actually the correction of that query. And if you see that over and over again across your user base, then you're able to come up with this, did you mean? And you'll be able to correct spelling without any semantic analysis. And this algorithm works across languages, doesn't matter which language you're doing this in. It just figures it out. It doesn't matter if it's a word that's not in the dictionary, it's a new word like that teenagers just invented, right? So that's the new concept of use all of your data, because if you use all of your data, you're able to achieve results that you didn't think of before were possible. The other one from the finance industry is fraud prediction. So typically the way we do fraud prediction in the finance industry is we try to map you to a cluster of users. So there's different spending patterns that different clusters of users have. Instead of trying to model each user by themselves, which is very expensive, used to be very expensive, we will try to map you. You belong to the single income family. You belong to the dual income family. You belong to this band, that band, this geography, and so on, to a cluster of users. And if we see you do a transaction that doesn't fit within that cluster, then we send you a warning, right? That's the old way of doing things. The new way of doing things, no, I'm gonna go model every user by themselves. I'll model you, your spending pattern, and what you're buying, and where you're going. So that when a fraud transaction comes up, it's actually very highly likely to be truly fraud transaction as opposed to an annoyance for you. So a very common thing that many of you might have experienced when you travel to another country and you use your credit card, many times your credit card company will block the transaction, right? Because of the clustered model they're using. If they're using a human model optimized for you, they would have seen that you just bought a ticket to go to that country last week. So obviously you are traveling to that country, it's okay for you to make the transaction. Right, so things like that, right? If you're able, we call that the long tail phenomena, right? The long tail phenomena meaning that we used to be able to fit our distribution and do our statistics, sample statistics on clusters of users when we had a small distribution of our users. But now we have a very long tail of users. We have some users that fit the model, but we have many, many users that don't fit the model. Or we have many products like Netflix, for example, many movies that don't fit the model, etc., etc. So these are the three concepts, and sorry if I dug too deep in each one of them, but they're really, really important, fundamental, behind this whole movement of big data. So number one is flexibility and agility, which is the kitchen thing I gave you. Number two is scalability, but that's scalability not just of machines, but also scalability of humans, meaning the same algorithms you write for 3 nodes, run on thousands of nodes, and then the economics of just keeping all of your data for all of your users for much longer periods. So that was the first half of the talk. The second half of the talk now, I'm going to dig deeper into CDH itself and then how Hadoop relates to relational database systems and how do you fit that in your BI infrastructure. What does the BI infrastructure look like in this world? So this is the main flagship product from Cloudera. This product is 100% free, 100% open source. We don't make any money from this. I'll explain to you later on how we make money, but we don't make any money from this. But invest a lot in it. We have many, many engineers working on this product. And the key point of this slide is Hadoop is just this, right? Hadoop is the kernel, just like Linux. When you go get Linux, you don't get Linux, the kernel. It doesn't work by itself. You want everything around the kernel that makes a functional operating system. So in the same way that Red Hat does that or Canonical does that for Linux, we do that for Hadoop. So we take Hadoop, but then we package around Hadoop a number of other projects that truly make out a functional data operating system. And that's what CDH is. CDH is short for the Cloudera distribution, including Apache Hadoop. And the reason why we say including is because it's one block in all of this. So you see we had other systems like Flume and Scoop for data integration. I'll talk about that later on. We have systems like Pig and Hive that make it simpler to write jobs on top of Hadoop. So Hadoop out of the box, if you want to write queries for Hadoop, you have to use something called Java MapReduce. Not everybody wants to write Java MapReduce. It's very powerful, very strong. You can do lots of sophisticated analysis with it, but you have to go learn a new language, Java, if you don't know Java already, and you have to learn a new programming model called MapReduce. With Hive, it's SQL. Hive just takes SQL. It takes your SQL, it compiles your SQL into Java MapReduce for you, so you don't have to go learn Java MapReduce. Not only that, Hive, through ODBC, integrates with MicroStrategy, which I'll talk about later on, and that's why I'm here today. Apache Pig is another language that makes it much easier to work with Hadoop. Edgebase is a very nice layer on top of Hadoop that makes it useful for serving. If you want to do online serving, real-time serving at scale, you can use Edgebase for that. I'll talk about Edgebase later on. I should note Edgebase, for example, today, the Facebook mail system, when you send messages in Facebook to somebody else on the Facebook platform, that all runs on top of Edgebase today. Millions of users running on top of the system. Again, it's an open source system, so Facebook contributes a lot to it in addition to Cloudera. We talked about Hive. Uzi is a nice workflow scheduling system, so if you have many jobs running inside your data flow, job 1, job 2, job 3, job 4, job 5. You can set up the dependencies between them. You can say only run job 3 when job 1 and job 2 finish. And when job 3 finishes, run job 4 and job 5. If job 3 fails, run job 3 again. That kind of stuff, right? So you can define all of that in USD, for example. And many others. The key point is it's really about having this complete framework that allows this platform to be functional for you. Again, the analogy is very strong with Linux, the kernel, versus Red Hat, the distribution. It's a very strong analogy there. For those who have been using CDH, I just want to highlight that we just released CDH 4, the newest version of CDH a few months ago. And the key improvements, there's many improvements, but the key improvements is much more stronger availability story. The performance has been improved almost 100%, and the scalability now of the system is more than it has ever been before. It can literally go to thousands of nodes. We had a limitation of 4,000 nodes. Now that limitation has been lifted. You can grow the system as big as you would like. There's many other benefits came with CTH4. So Edge-based. Edge-based is a very important system. That's why I want to highlight it specifically. Also in the BI world, it has lots of importance as well. HDFS, the storage system, is optimized for very large files, optimized for sequential access, and optimized for append only. So actually in HDFS, when you create a file, you cannot go and change things in the middle of the file. You can only add things at the end of the file. If you want to change things, you have to create a new file from your old. You have to transform the old file into a new file. So that's what HDFS has been optimized for. So it's very good for fact tables, because that's usually what fact table is. Fact table is something you're adding more facts at the end, and you're typically doing very large sequential scans on top of fact tables. Edge-based, on the other hand, is a system built on top of HDFS. It's built actually based on another paper that Google published called the Google Big Table. And essentially, it's a memory-based system that leverages memory across a cluster of machines to significantly reduce latency and to provide update semantics. So Edge-based is optimized for small records. It's optimized for random access, so not sequential. If you do sequential in Edge-based, you get lower performance. If you do random in Edge-based, you get more performance. And it's optimized for atomic record updates. So you can actually update things in the middle in Edge-based. You can do an insert, update, or delete in the middle, not just at the end. So it's very useful for dimension tables, right? Like zip codes and user IDs and so on, right? Things that you're updating continuously and that you're doing a drawing from that dimension table into your fact table, and you're looking all over random access on the dimension table. So that's kind of the analogy of Edge-based to HDFS. So this is how Hadoop fits in the enterprise data stack. I'm not sure we're still working, like our marketing team is still working on a term, what to call it here. It's not data warehouse, right? So we're thinking data hub, data dump, data landfill. Our marketing doesn't like that one. But it's a place where you can just put all of your data, right? You can store all of your data. So you have your unstructured data sources like web data, files, and logs, and we have a system called Flume that helps you to collect all of these. You have your relational databases, when you have Scoop. Scoop is a very nice tool that lets you just point at a table inside your database and give it a credential. It will make an image of that table inside Hadoop. And then you put all of that inside here, right? And then you use something like Informatica or Talent, both of them have good integration right now, to define your ETL logic the same way you define your ETL logic today. However, the execution of that ETL logic will be pushed down here, right? So, you know, as Informatica and as other ETL tools struggled with scaling, what they did is our industry shifted from the ETL model to what we call the ELT model, right? Is we pushed the transformation to happen inside these guys. These guys were not built to do transformations. They were not. By pushing the transformations inside here, whether it be Oracle, Teradata, or whatever, first you're creating this column called blob where you're loading all of the stuff that you want to transform. So you're not leveraging the schema inside the system. But second, you actually slow down your operational queries by having the transformation happen in the same system as the transformation workload. So with the Hadoop, you're able now to push the T to happen down here, right? So you define your workload with Informatica or Talent, and then they now have integration where their engines are embedded inside the computational engine for Hadoop. So your transformation happens inside here. I'll give more detail on that one for Informatica later. And then once the transformation is done, you now have both, and I should amend the slide to show that, but you have both the original unstructured data on one side, but inside the same system you also have the structured data. So Hadoop can store structured data. Hadoop does have SQL in it, and it can store structured data. So once you have the structured data here, then you use Scoop to copy that structured data from your from the system inside your enterprise data warehouse. Okay? And then now you can use MicroStrategy to access both types of data. You can use MicroStrategy to access your most recent data that you have down here, but you can also use MicroStrategy to access your full history, whether it be the full history of the structured data or the full history of the unstructured data. Right? And a question will be asked, why do you still need both in this case? And I'll comment on that later on, so hold on to that question. But the other nice thing is not only can you go with MicroStrategy, because Hadoop speaks ODBC and SQL, but you can also go with other development environments as well. Like you can go in with ETL tools and run things inside. You can go in with Revolution Analytics is a company that commercializes R. Can I get a show of hands? How many of you know about R? That's very good, so 60% of the room. R is a very famous open source data mining library that now has full integration with Hadoop. So that you still use R in the same way that you do, but it pushes the execution to happen in parallel inside Hadoop, so you don't have limitation based on the memory you have in your R clients. So we have integration with them right now. Karmasphere is a very nice IDE, integrated development environment for writing Java applications across your data. So if you want to do the heavy lifting, if you want to do image recognition, facial recognition, et cetera, much more heavier kind of stuff that doesn't fit in SQL, you can do that as well. So you have the freedom of all of these frameworks running on top of your data, as opposed to just SQL. So this is the integration with MicroStrategy that we have. MicroStrategy, as you know, supports what's called multi-source. You can have a data model in MicroStrategy that points both towards a relational source like Teradata or Oracle, but also points towards a system like Hadoop as well. So for example, if you're running your query and you're only looking at the aggregates and the high-level information, then the multi-source model will detect that and will send you here. And once you start doing drill down, I actually now want to see the event level detail, every single bit of data I have, it will detect that too, and it will send you down here. So depending on your query, it will automatically send you to the system that has the data for you. Same thing with history. So I'm only going to keep a year of data here, and then I'm going to keep 12 years of structured data here, right? Because the economics work. Same thing, if you query over the last year, it will go here. Once you start going over more history, it will go down there. So you get the best of both worlds, right? That's the key point, is you get the best of both worlds. With Informatica, that's the integration we have with them, and Talent has a very similar integration as well. But essentially, using your desktop, Windows or whatever, you can use, Informatica has this thing called Edge Parser, but they're also adding this to Informatica 9.5 will have this built into the main Informatica Studio as well. But with Edge Parser, it's a graphical studio. You can build your ETL logic, define the transformations and all of that stuff, and then it outputs this thing called the transform definition, which you then load inside your Hadoop cluster, runs on parallel across all the nodes, and executes the transformation inside the cluster. So you don't do the transformation over the network, which slows things down. So Informatica has that, and again, it will be much more streamlined. In Informatica 9.5, all you're going to have to do is the same transformation that you have been doing, push up ETL, push up ELT inside your Teradata system. You can just do push down inside your Hadoop system, and it will just do transformations down there. So this slide is about using the right tool for the right job, and answer that question. So why do I still need both? Why should I still use a database and Hadoop if Hadoop can do SQL? And there's two reasons for that. One reason I covered already before, right? Which is two slides for that, I guess. One slide I covered already before, which is the kitchen slide, right? The agility slide. The schema on write versus schema on read. Okay? By having schema on write, by at load time defining your schema and structuring your schema, you're able to lay down the data much more effectively, and hence you're able to do interactive queries much more quicker because you already parsed your data at right time. Okay? So that benefit exists for databases. That's why I use this analogy of a sports car versus a cargo train. So relation databases are like a sports car, right? A sports car is very good at getting from 0 to 60 miles per hour. A train can never get from 0 to 60 miles per hour in the same time as a sports car because of how much momentum and inertia the train has to overcome to get going. Which is the parsing, in the Hadoop world, that's the parsing cost. The parsing cost of parsing your data, because we're doing that parsing at read time, we have to overcome that parsing cost. So any query that executes in less than the time it takes to parse data, obviously the parsing cost will overwhelm, and you will see that. So the interactive stuff is not very fast in Hadoop. But once the train gets going, not only is the speed of the train much higher than a sports car, the capacity, the throughput of how much a train can carry is also much higher than a sports car for the price. Right? You can still go buy 100 sports cars and link them together and make a very long train. It's not going to be a very efficient train economically speaking. So that's a very key distinction. Is Hadoop is not good. It's not good at interactive OLAP. If you want to do interactive OLAP, you still need these guys. This is what these guys have been built for. They have been built for interactive OLAP. Hadoop is really good at transformations, right? So we want to use Hadoop for transformations and for the agility of discovering new things that we don't put in our main data model yet. So we have that bridge. And once we find a repeatable thing that now should be part of our interactive dashboard in OLAP, then we do that. Then we move it into the other system. We want to have the freedom of both. So that's number one, right? So interactive OLAP, like if I have a customer asking me, can I use Hadoop for interactive OLAP? I'll say no. You can't use Hadoop for interactive OLAP. If you want to do interactive OLAP, you have one of two choices. You can either go and augment Hadoop with a relational database system, or you can use Microstrategy or like any of other BI system. But Microstrategy specifically, as you know, has the intelligent cubes, right? So you can preload your intelligent cube overnight, and you do the in-memory OLAP in Microstrategy, which is actually quicker than doing it in your database, if you do that. So that you have to use one of these two options. That's number one. Number two, if you want to do multi-step ACID transactions, you can't use Hadoop. So Hadoop does not have multi-step ACID transactions. So what is that? That is begin transaction, run a select statement, do some updates, do some inserts, do some deletes, a cursor, end transaction. That's called multi-step ACID. That's what databases have been built for. And that's what slows them down, by the way, in terms of scale. But it's a very important functionality. But that's why they can't scale, because it has very complex locking to be able to assure that for you. So Hadoop doesn't have that. Hadoop does have single row transactions. So in Hadoop with HBase, for a single row, you can have multiple clients trying to update that row, like your email message in Facebook, for example, and it will be consistent. It will be serialized, and the access will be consistent and atomic at that level, but only at the row level. You cannot do it at a multi-statement level. And then last but not least, is Hadoop is not there yet in terms of SQL compliance. So if you want 100% NC92 or NC99 SQL compliance, then you should use one of these tools because they have been around for much longer than Hadoop has. Hadoop is getting there, but it's not there yet. On the other hand, if you want to be able to deal with data of any type, whether it's structured or not, if you want to be able to scale to 100 petabytes in a single system at economics that are a fraction, and if you want to be able to do things beyond just SQL, if you want to do SQL, but you want to go beyond SQL, you want to do advanced data mining with R, you want to do image processing, video processing, OCR, etc., then you go with this. And in fact, Oracle, we have a very strong partnership with Oracle, where Oracle now sells a appliance called the Oracle Big Data Appliance. The Oracle Big Data Appliance is based on the extreme, what's called? Exadata, the Exadata system, right? The same hardware used for the Exadata system and the Exalogic system. So it's very highly optimized hardware that runs inside it CDH with all of the Hadoop components, but also includes other things from Oracle as well, like Berkeley DB, which is now the NoSQL database. And Oracle has accounts where they have both. They have the Exa data system running side by side with the Hadoop system because they complement each other. They're actually very complementary to each other. So before I conclude, I have a couple of slides and then we'll let you go eat because I think it's lunch time. So the question we frequently get asked, if CDH is 100% free, 100% open source, 100% Apache, how does Cloudera make money? Right, and we make money by just taking money from VCs, I guess, and spending the money. But that was true 4 years ago when we just started. We are now 4 years old. The company Cloudera is 4 years old. We have more than 250 employees worldwide. We have more than 300 partners, including big ones like Oracle, Dell, and others. Microstrategy, obviously. And we have many customers across many verticals. So this is not just a web-based technology. This is a marketing slide. Okay, so this is not just a web-based technology. This is a technology that applies for government, applies for finance, applies for. We have customers in agriculture now using this technology, to my surprise. So how do we make money? The way we make money is very similar to Red Hat. It's not exactly like Red Hat, but it's very similar. So we have this free thing, which is both option 2 and option 3 here. We have this free thing called CDH, which is our distribution, right? 100% open source, 100% Apache, 100% free. Developers like that. Developers like free stuff, right? Because they don't like to pay for stuff and sometimes don't have the money to pay for stuff. So by having it free like that, it spreads virally inside organizations. You get organizations where Hadoop starts to spread virally and people really get to see how valuable it is and how it solves real use cases for them. Once Hadoop goes production, once it becomes running in a mission critical environment or a production environment, just like with any other software, you cannot have software, or actually even hardware, running in production without a maintenance contract on it, in case something wrong happens, right? In case something is slow, there is a failure, there is an error message that you know what it means, etc., etc. Right? So it's very similar like me telling you, hey, if you look under your chair right now, I have a key for an airplane for you outside. It's a free airplane, take that airplane. You're not gonna think that I'm not gonna pay any money for that airplane going forward. In fact, you pay more money for the maintenance of an airplane than the airplane itself over time. So it's very similar to that. But in addition to the maintenance that we provide to you, just like the maintenance you would get from Oracle or from VMware or from any other commercial vendor, so there is no upfront license, but there is a maintenance on the software once you have it running in production. We also give you a very special piece of software called Cloudera Manager. And Cloudera Manager is a management console for Hadoop. So if you know VMware, there is VMware ESX, the virtual machine, and then there is a vSphere or vConsole, which allows you to manage the virtual machine because you have a jungle of them out there, a jungle of virtual machines. And the same thing, you have a jungle of Hadoop nodes out there, and you want to have the central place where you can control all of them, deploy them, optimize them, control them, predict failure before it happens, etc., etc. Cloudera Manager is proprietary, so you only get Cloudera Manager as part of this subscription with Cloudera. So that's pretty much our business model, right? So we have CDH, which is free, and that helps the software spread across the world, and also helps us reduce the development costs. So Hadoop is open source. We have almost 100 developers at Cloudera working on the system, but there is other companies like Facebook investing almost 50 developers working on HBase and Hadoop. Yahoo had a big arm that now got spun off that also is investing a lot of effort building the Hadoop system. We're seeing new companies like Microsoft and IBM and Amazon jump in and start to contribute to the Hadoop system as well. So that makes the cost of building a system much lower for us and for you, which we pass along to you as well. So that's kind of the business model for the company. Sorry for boring you with that, but so once you have Hadoop running in production and it's mission critical, that's when we love to get a phone call from you to help make sure you're successful. Now there's many books where you can read more about Hadoop. There's the main Hadoop book, which by the way was written by one of the engineers at Cloudera. There's the Hadoop operations book, also written at Cloudera. Pig, HBase, Mahout, which is the data mining library built from the ground up for Hadoop. We have a website called university.cloudera.com, has many free videos for learning more about Hadoop. So if you want to learn more about the different system components, you can go there, access these videos. But we also have training that we give worldwide, including Europe, almost every other week now. So you can access the schedule for that and sign up if you would like. There is a very big event that we are hosting with O'Reilly next 2 months from now, October 23rd, that's 3 months from now. So highly recommend you take a look at that. Many big enterprises are coming in and talking about their stories of how they're using Hadoop. But this conference is more than just Hadoop. This conference is really about big data science, but Hadoop is a big theme of that conference as well. So with that, I'm going to conclude. Remind you with the 3 key themes. The 3 key themes of why Hadoop is really taking the world by storm. Number 1 is the agility it provides, right? Is that the fact that it can grow at the speed at which your data is growing, but more importantly, at the speed at which your data is changing. Number 2, scalability, and again, scalability of technology, but also scalability of humans. The same code you write for a few nodes runs for thousands of nodes. And economics. It brings down the economics of keeping your data to a level where you can actually keep all of your data and access all of your data to solve your problems, which gives you a new way to think about how can you solve problems with your data. And then I have a commercial blurb about why Cloudera is great over here. The marketing team makes me great. So yeah, I mean, we're number 1 in this space. We've been around longer than any other company. We were started 4 years ago, just 4 people 4 years ago. Today we're more than 250 across the world. We're the only ones that have something like Cloudera Manager that makes you support yourself, because guess what? The quickest way for you to resolve a problem when you have a problem is you fixing it yourself. So with Cloudera Manager, we take all the knowledge we have from our customer base and we put that inside Cloudera Manager. So you can very easily debug, fine-tune across the whole stack, all the way from the lowest layers, HDFS, MapReduce, Big Hive, all the way to the higher level metadata layers as well. Our team has been doing this across many industries, and we have a very big partner ecosystem. I mean, Microstrategy being one of our best partners that we work with, as an example. And the key there is just when you're running in production, once you're ready, we want to be there with you to help ensure your success. So with that, I want to thank you very much. I'm going to let you go get lunch. If you have any questions, I have a bunch of business cards up here. you're welcome to grab one and email me later, or you can ask me right now. So thank you very much.